In this video, we're going to be talking about the change of variable and principal axis theorem relating to quadratic forms. So in our last video, we briefly explained what a quadratic form is. A quadratic form would be something like, x squared plus y squared equals, 1. That's a quadratic form. And what we're doing with symmetric matrices is we're representing quadratic forms. So in this case, our matrix would look something like this. We're using symmetric matrices to represent quadratic forms. In the last video, I mentioned that this is useful due to various properties of symmetric matrices, and in this video, we're going to explain why and how we can use some of the properties of symmetric matrices. But before we do that, let's take a problem. Say we have x squared minus, let's say 4xy plus 4y squared. And we want to know if this is always greater than 0. But that's a bit hard to do at first, especially if these numbers are bigger, because we have to figure out whether this part of the quadratic form is, which clearly may be able to be negative at some points, is always going to be greater than these two. And the way we can figure this out, for especially some of these larger ones, is by using symmetric matrices, because A, in this case, can be written as 1, 4, minus 2, minus 2. And if you take A transpose, you'll find that it's 1, 4, minus 2, minus 2. So it's definitely symmetric, and it's always going to be symmetric. And we remember that we can diagonalize A using its normalized eigenvectors and its eigenvalues to create a new, just a representation. And if we do this here, we can essentially, because remember D is just the eigenvectors, the eigenvalues on the diagonal. And notice that there's no what we call, I think it's the cross product, or the middle term, I guess, works as well for a 2 by 2. So let's go and try something. If we write x to be py, then we can rewrite x transpose ax to be, well, the first thing we can do is we can write py transpose a py, which is equal to y transpose dy. Right? So, and d is just our eigenvalue. So if we find our eigenvalues and our eigenvectors of this matrix we're trying to solve, let's use this one here, we can create a symmetric matrix in the middle of the quadratic form that's much easier to interpret. So let's take a look at this. So we've got A here. What are the eigenvalues of that? Well, let's just use the characteristic equation, because even if we can do it by observation, let's use something we know. Lambda squared minus 5 lambda plus 4 minus 4, so with lambda minus 5. So we've got 5 and 0. Oh, right, of course, because it's singular. So if we just do 5, 0 there. And before we even calculate what our normalized eigenvectors are, we notice something, that we've removed these middle terms. Now that's quite important, right? Because once we put our vectors in, we're no longer going to have a middle term. And I think what we end up with is something to the effect of 0y1 squared plus, I think it ends up just being 5, or maybe it's 10 y2 squared. And that must be positive, because the only terms in there are positive. And if that is equal to this, and this is equal to that, then this is always positive, which means that this is always positive. So we can see how we've been able to use this change of variable operation to solve a problem that would probably have been a bit different if we didn't leverage some of the properties of symmetric matrices. Now, obviously, these quadratic forms are sometimes not zero, they're sometimes less than zero. In this case, we've identified that it can be zero and it can be positive, but it can't be negative. And in future videos, we'll kind of describe what that means and what that can tell us. But anyway, in this video, we explored how a change of variable operation can manipulate a quadratic form to reveal various things about it, and how we construct a change of variable operation using what we know about orthogonal diagonalization of symmetric matrices. Thank you for listening.